right. Discrete Math. Friday, March 20th. Last day of the first week of the coronavirus quarantine. Okay, so let's jump in here. The goal today is to kind of finish off the probability stuff, maybe start a little bit of the statistics discussion that will finish the course. But today I want to finish off the fundamentals of probability that we have been spending several lectures on here. So that said, here we go. Okay, Bayes' theorem is the last thing I want to talk about. It's a very important theorem. Has a lot of far-reaching consequences. There's been a lot of mistakes that have been made over the years because people haven't really understood what Bayes' theorem is saying precisely. Okay, and we'll get into what that is exactly, or else people are just totally unaware of the fact that Bayes' theorem is a thing at all. Okay, so there's been a lot of mistakes that have been made in the past because people haven't been more acutely aware of what of this particular theorem and what it is saying. Okay, so in brief, let me just say that what Bayes' theorem says or allows you to do is it allows you to take a conditional probability, like the probability of A given B. Actually, here I'm going to go like this. It's like if I wanted to do the probability of A given B, so basically Bayes' theorem works on the assumption that you know the probability of A given B. Okay, so the probability of A given B. Okay, so you know what that is. So Bayes' theorem allows you to compute the conditional probability in the opposite order. So the probability of B given A equals what? Okay, and that's what Bayes' theorem allows you to do. So that's kind of the essence of Bayes' theorem. Okay, so whatever else transpires after this point, just know that in the end, that is the essence of Bayes' theorem. It allows you to kind of flip the conditioning around. Okay, so long as you have enough information to do that, but it's less information than you might think you would need. Okay, so let's go back over to here. Okay, so Bayes' theorem says that, but here first, before we get there, there's a few things we need to consider. So for instance, there's this thing called the law of total probability, the law of total probability, which basically says that suppose I have kind of taken the entire sample space and split it up over some number of mutually exclusive and exhaustive events. That means that those events, A1 through AK, eat up the whole sample space and do not overlap with one another. So they're kind of like atoms of the entire sample space, okay? So, you know, the picture I have in my mind is not unlike the picture that that we were dealing with the other day. So let me see here. I'm going to go right here on the board and kind of talk to you about this right here. So remember when we were doing stuff with that credit card problem, and by the way, I mean, there's a quiz that's going to be due, Friday. on that exact problem where you compute the probability of a credit card. But one thing that I would point out is we drew a picture like this at some point. We had the entire sample space, and we kind of split the thing up into three sets like this, right? So in Bayes' theorem, you're kind of starting out with a partitioning of the sample space like this. I mean, there might be more than three sets, but you know, I said that there was K in general. And the law of total probability says, all right, if I have some kind of event, B, now remember this looks exactly like the sort of thing that we were doing with the credit card problem, doesn't it? So if I have some event B, then I can compute the probability of B in this way. So the probability of B is obviously equal to the probability, well look, I mean, I just need to intersect it. I need to just intersect it with each one of these and add those together, right? The reason I can add them together is because there's not like any overlap between A1 and A2 and A1 and A3 and A2 and A3 at all, okay? So it's gonna be the probability of B and A1 plus the probability of B and A2 plus the probability of B and A3, okay? And then you say to yourself, all right, well, what in the world is the probability of B and A1? Well, I could write that using conditional probability. So it's like the probability of A1, so it's the probability that A1 happens times the probability that B happens given that A1 happened, plus, okay, this again, this is just a recasting of the probability of B, plus the probability that A2 happens times the probability of B given A2, plus the probability of A3 times the probability of B given A3. That is the law of total probability, okay? The law of total probability. So the assumption again, okay, that's the formula that you end up with here, is that the probability of B is equal to the sum of these various probabilities. But the assumption was I had three sets that were kind of the atoms of the sample space itself. They exhaustively covered the whole sample space and they were mutually exclusive. They did not overlap with one another, okay? So that's kind of what, oh man, sorry guys. That's what this, this law of total probability is saying here, okay? The law of total probability is saying that you have K things that cover the whole thing, K things that cover the whole sample space, and I need to make this a little bit smaller, sorry. Okay, I have K things that cover the whole sample space. They're mutually exclusive, and if somebody hands me an event B, then basically I can do a thing similar to what I just did here with three things. Now, the most common situation one encounters is when there's actually only two sets that are covering the whole sample space. So like A and its complement, for instance. Okay, so this is the most common situation. In fact, I'll kind of draw that over here on the left side of the board. So the most common situation is this. Here's the sample space. Here's A. Okay. And of course, the rest of it is just A prime or A bar, okay, depending on how you want to notate that. And here's B right here. I just always kind of start over again in some sense. I kind of start over and just think about it. I don't like memorize the law of total probability. So the probability of B is equal to the probability of B and A plus the probability of B and A prime. okay, which is equal to, okay, so the probability of B, these guys are equal to, well, it's the probability that A happens times the probability of B given A, okay, that's the first summand, plus the probability of A prime, right? So the probability that the opposite of A happens times the probability of B given A prime, okay? This is the most common version of the law of total probability that people utilize, where you just have two sets, kind of making everything up. Okay. All right. Back in here. All right. So there we go. So that's the law of total probability. Hopefully that kind of makes sense. That's an important thing to have in mind here. Okay. Oops. Actually, I'm going to have to. This thing's all messed up. I'm sorry about that. Okay. Hang on. I'm going to pause this for just a minute. All right. Sorry about that. Technical difficulties. That's just the reality right now. Sometimes things like that are going to happen. So what happened was when I unplugged my machine from the network over there, I lost access to my files. But I'm back up now. Okay, so what I want to do is to share this with you. And we will continue. There it is. Okay, so the law of probability says this. Okay. And so we're going to use that to do what I promised at the beginning, namely, flip conditioning around. And here is the statement of Bayes' theorem. Okay, so it says, again, we start off with a collection of atoms for a sample space. That is, these things are mutually exclusive and exhaustive events. And we know the probabilities of those events. So, oftentimes we call those prior probabilities, okay? So we know the probabilities of these various events. That's kind of like in that credit card problem we had earlier. I knew those probabilities of like, being a regular customer, plus customer or a premium customer, okay? So then for any event B, for which B, the probability of B is positive so that it makes sense to condition on B, the posterior probability of AJ given that B has occurred is, okay, so that is, I can actually compute the probability of AJ given B, which is given by this formula, okay? Of course, this is just the formula for conditional probability, okay? Well, and what's the top? Well, the thing is, so here I was conditioning on B, and the thing is, it might not be easy to, we might not know off the top of our head what the probability of B even is necessarily. But I do know the probability of the AJs, okay? So this is equal to, look, the top thing, that's just, it's like the probability that AJ happened times the probability of B given AJ. And then on the bottom, all I've done is I've used the formula for law of total probability. P of B is going to be equal to the sum of these things. That's just the law of total probability. And so what we have done here, in effect, is we have taken the probability of AJ conditioned on B, and we've used the conditioning flipped around to compute that. So it's B given AJ, and there's B given all the other things as well. So the thing is, when you use the Bayes theorem, what you're in essence doing is you know lots of stuff about the atom sets, right? The AIs. And you even know some conditional probabilities of those things. And you use those conditional probabilities and the probabilities of the individual AIs to get the probability that those atom sets happen given the other event. Okay, so that's sort of amazing. You've in effect flipped the conditioning around. And that might seem sort of mysterious. And by the way, this formula is not very mysterious, right? So I just use the formula for conditional probability. And then I use this law of total probability on the bottom to rewrite this. And upstairs, what I did is I said, well, you know, the probability of AJ and B, what is that? Well, it's the probability that AJ happens times the probability that B happens given AJ happen. Okay, so this formula makes sense. You think about it. And this might feel somewhat mysterious, like, okay, why would this be useful? But we'll see some examples for why it is useful here pretty soon. Okay, so like here's an example right here. Okay, 70% of the light aircraft that disappear while in flight in a certain country are subsequently discovered. Okay, of the aircraft that are discovered, 60% have an emergency locator, whereas 90% of the aircraft not discovered do not have such a locator. Okay, suppose a light aircraft has disappeared. Okay, so again, let's write down the information that we have. I'm going to do that. So 70% of the light aircraft that disappear while in flight in a certain country are subsequently discovered. Okay, so I'm going to have to be careful here. Looks to me like we are basically going to be breaking down our sample space into two pieces. Okay, so this is our sample space is the collection of all airline things, of all aircraft that happen to have disappeared. Okay, so these are aircraft that happen to have disappeared. Okay, 70% of light aircraft that disappear while in flight in a certain country are subsequently discovered. Okay, so let's let D be this side. Okay, so D means that they've been discovered. And let's let D prime, of course, means that they're not discovered. Okay, so D is discovered. D prime is not discovered. Okay, so all of these aircraft have disappeared. And incidentally, we have some information here that we're going to write down. Okay, 70% of light aircraft that disappear are discovered. So the probability of D, the probability of discovery is 0.7. And I know that this is a teensy screen here, but just bear with me. I want to make it big in just a minute here. And of course, that means the probability of D prime is equal to 0.3, of course. Okay, of the aircraft that are discovered, 60% have an emergency locator. Okay, so of the aircraft that are discovered, so given that an aircraft has been discovered, 60% of those have an emergency locator. So the probability of a locator given that it was discovered, so of the aircraft that are discovered, so the probability of a locator given that it's discovered is equal to 60%, is equal to 0.6, right? So this L right here stands for locator. Okay, so they actually have a locator. Of the aircraft that are discovered, 60% emergency locator, whereas 90% of the aircraft not discovered do not have a locator. Okay, so that means the probability of L prime, given that they were not discovered, so they don't have a locator, given that they weren't discovered, That is like 90%. Okay, that is like 90%. And I'm going to erase this and expand this board so that you, or expand the screen so that you can see what's going on here a little bit better. So again, there's the sample space. We've split it up into D and D prime. Those are obviously mutually exclusive and exhaustive. They exhaust the whole sample space. D is the discovered aircraft that have disappeared, and D prime is the not discovered aircraft. Okay, we were told that if an aircraft disappears, that's our sample space. They're just the aircraft that have disappeared. That 70% of those are discovered, and 30% are not discovered. And we were told that of those that are discovered, so now I'm kind of zooming in to the discovered part of the sample space. Over here I go, that's the new sample space. That's what we mean by conditional probability. The probability that an aircraft has a locator, given that it was discovered, is 60%. And the probability that there is no locator among those aircraft that were not discovered, that's 90%. That's a 90%. And by the way, you know a lot of other things here as well. Okay, for instance, what is the probability of there being a locator, of not being a locator given that they're discovered? Well, the probability of there being a locator was 60% among those. Okay, so that means the other 40% would not have a locator. The other 40% among the discovered aircraft. Okay, and what about the probability? What about the probability of L given D prime? That's the other one. So among the aircraft that were not discovered, what's the probability of there being a locator? Okay. What's the probability of there being a locator? Well, 10%, because it was 90% that there wasn't a locator. Okay. All right. So that's interesting. Now, I mean, one might kind of question how you would even have this data, but we're just making stuff up here. So bear with me, right? So how in the world would I know if there's a locator? I guess that could be part of the aircraft manifest or something. So yeah, I guess it makes sense, right? So that's fine. All right, let's see what they're going to ask us to do here. It looks like we have a lot of information. Let's see what they are going to ask us to do. Okay, so I want to share this again. Okay, share. Yeah, okay, so let's see here. What is the probability that it has an emergency locator? Okay, so we're imagining that we have an aircraft here that has been, okay, so let me just kind of move my screen here a little bit. Okay, so what is the probability that it has an emergency locator? So we have a randomly selected light aircraft. What is the probability that it has an emergency locator? So I want the probability of L. I want the probability of L, basically. Okay. What is the probability of L? What's the probability of there being a locator? Well, okay, so I mean, if I were in this picture over here, this would be L. Okay. I could, think of L being split up among these couple things here. Okay. So if the thing has a locator, then either it wasn't discovered or it was discovered, which means I can write this as the probability of L and D plus the probability of L and D prime. Yeah, hopefully that makes sense. And then I can say, well, I have all of this information over here, like the probability of D, probability of D prime. I have all those conditional probabilities. So it seems like I should be able to compute this. Know what I mean? Yeah, so the probability of a locator, you know, this first guy right here, I could think of it as the probability of D times the probability of L given D. Okay, that's what the first thing is, probability of L and D happening. You think of D happening and then L happening given D, that D happened, plus the probability of D prime times the probability of L given D prime. Okay, there's that. Okay, and that, so what is that going to be equal to? So the probability of D is 0.7. Okay. The probability of L given D, well, that's right here, right? So that's 0.6. Okay. Okay, plus, what's the probability of D prime? Well, that's 0.3. You see that right there. Okay. And then the probability of L given D prime, that's one of the last things we wrote down on the board. Probability of L given D prime is 0.1. Yeah. 0.1. Okay. Interesting. Okay, so 7 times 6, 42, so that's 0.42 plus, you know, so it's 0.03. Okay, so it's 0.45. Okay, so I'm actually going to write that way up here at the top. 0.45 is what we're going to get. We're going to write this way up at the top in case we need to reference this later on. Basically, to do this, we actually used the law of total probability. Okay, we used the law of total probability. Okay, if it has an emergency locator, what is the probability that it will not be discovered? Okay, if it has an emergency locator, what is the probability that it will not be discovered? So look, I'm going to erase this stuff. Okay. And they're asking me, okay, if it has an emergency locator, what is the probability that it will not be discovered? So what am I being asked here? I'm being given that it has an emergency locator. Given that it has an emergency locator. So I want the probability of something given that it has an emergency locator. Okay, so what is it? What is the probability that it will not be discovered? So the probability of D prime given D. Well, now I'm gonna use Bayes' theorem. Okay, Bayes' theorem says that that this is like the probability of D prime. Okay, well, first of all, this is just the formula for conditional probability. The probability of D prime and L, okay, divided by the probability of L, which I have. It's right up here. Okay, and we already computed that. Part of Bayes' theorem is that, you know, you use the law of total probability to compute the denominator. We already did that. We used total probability to pull that off. So what about the top? Well, let's see. I have the probabilities of L given anything, given D or D prime, right? Those are in my, within my grasp. So I'm going to say, you know, first I'm going to say, well, it's the probability of D prime times the probability of, okay, this means not discovered, okay, times the probability that there is a locator given that it was not discovered, okay, which I actually have that down at the bottom, and this is divided by the probability of L, okay? And I think that we have all these things. So the probability of D prime, for instance, is right there. It's 0.3. Right, so this is 0.3. What is the probability of L given D prime? Well, the probability of L given D prime is 0.1. Okay. And on the bottom, it's 0.45. okay, 0.45. Okay, so I'm going to have 0.03 over 0.45. Okay, so this is like 3/45. 3/45, which is like 1/15. Okay, 3/45, which is, I think that's 1/15. So what does that tell us? That, remember what we were computing? We were computing the probability that given that an aircraft has a locator, that it will not be discovered. And it turns out that happens about 1 in every 15 disappearances, which is kind of, I guess, what we would expect. We would expect that to be fairly rare. If there's a locator, we would expect more often than not that it would actually be discovered. So once again, we've taken all of these conditional probabilities that were flipped in the other direction, and we've managed to flip it around the other way. And that's what Bayes' theorem essentially enables us to do. Okay, if it does not have an emergency locator, okay, let me write down this one. So the probability of not being discovered, given that it has a locator, is 1/15. Okay. And let me erase this. If it does not have an emergency locator, what is the probability that it will be discovered? Okay, so now we want the probability of discovery given, okay, this is the other situation that might be, that we might be interested in knowing. Up here we just computed the probability of not being discovered given that there was a locator. Now we're being asked, look, if you don't have an emergency locator, what are the odds that you will actually discover this thing? Okay, so no emergency locator, what's the probability you're going to discover that thing? Well, once again, we're going to use Bayes' theorem. It's going to be the probability of D and L prime divided by the probability of L prime. You say to yourself, okay, I know what the probability of L prime is, right? Because you know what the probability of L is, you know what the probability of L prime is. The probability of L prime is equal to 55%. Okay, it's 1 minus the probability of L, which was 45%. Yeah. Okay, so I know that. So what? So I need to know, okay, all right, I have all of these conditional probabilities over here. So it seems like I should do the probability of D times the probability of L prime given D, no locator given that it was discovered, divided by divided by the probability of L prime, which is 0.55, okay? Okay, so let's see here. Probability of D is 70%. You see that over there, okay? 0.7. The probability of L prime given D, that's right there, 40% over 0.55. Okay, so that's 0.28. Okay, so 0.4. So that's 0.28 over 0.55, which is 28/55. Just barely over 50%. I don't think you can reduce that because that's only divisible by 5 and 11. That's 4 and 7. Yeah, so that's the probability. That's the probability right there. 28/55, barely over 50% chance of discovery if the thing doesn't have a locator. So I guess that's also something that we would have expected. Okay, so let me move this out of the way. Okay, put it over here. And let's move on. I think I'm actually going to not do this last problem. Okay, I think that last one's a pretty good place to stop. Look, you might say to yourself, when would this ever actually be useful? Well, it turns out it's very useful because, for instance, here's kind of a classic example. Someone might actually want to develop a pregnancy test to go to market with, okay? So what they would do is they would, to make sure, to see how well their test actually works, they would administer the test to people that they knew were pregnant. And the test had better come back positive a high percentage of the time because it's supposed to detect pregnancy after all. So that is, they would know the women were pregnant and they would administer the test and actually find the likelihood that the thing comes back positive. So they would be computing the probability of the test being positive given that the individual was pregnant. And they could also gather the data on non-pregnant women, right? Because there the test would need to come back negative. So, so they would gather a group of you know, non-pregnant women, and they would administer the test, and it had better come back negative a huge percentage of the time. So they're able to, just through you know, gathering data, find the probability of the test being negative given that the woman is not pregnant. Well, pregnant and not pregnant exhaust the sample space of all women. Pregnant, not pregnant, exhaust the sample space of all women. So you would have these probabilities, and by the way, you could also say, well, on average, the percentage of pregnant women is this. So then you would also know the percentage of not pregnant women. This is just, you know, on average, you know, in a moment in time, what is the average percentage of women that are pregnant and not pregnant? Okay, so you would have the probability of positive given that they're pregnant, which means you would also know the probability of negative given that they're pregnant, because you would just take the 1 minus that. You would have the probability of negative given that they're not pregnant, and you would also have the probability of being positive given that they're not pregnant. Okay. By the way, negative given that they're pregnant, that's called a false negative. You've probably heard that term before. You know, the test is telling you the condition is not present when in fact it is. Okay, that's a false negative. The situation where the test comes back positive when the woman is not pregnant, that's a false positive, right? Because the test is saying that the condition is present when in fact it is not. Okay? Okay? Or actually the condition is present when in fact, yeah, right. So it's a false positive. Okay? So you have the probability of pregnant, not pregnant. You have the probability of positive and negative given that they're pregnant. You have the probability of positive and negative given that they're not pregnant. That's a lot like what we have over here on the board behind me. And then what you can do is you can administer the test and you can predict what's the probability that if the test comes back positive. So you can flip the conditioning around. That's how you want to do this in the marketplace anyways. The only reason someone would take the test is because they didn't know they were pregnant. That's the whole point. Yeah. So they take the test, it comes back positive. So what information do we have? Well, it came back positive. So now you want to know what's the probability that I'm actually pregnant given that this thing came back positive. Or you might ask the question, the test came back negative. So what's the probability that I'm actually not pregnant given that the test came back negative? And Bayes' theorem allows you to compute those probabilities with the conditions flipped around from what you had at the beginning. So that is the power of Bayes' theorem. Okay. So I think I'm going to stop this for now. Hopefully that was an enlightening discussion around that. It's a nice thing to have at the end of our discussion on the fundamentals of probability. We will start statistics next. Bye.